let's talk about kinetic theory of gases. All right, so there's going to be four main ideas down here that I would suggest you memorize about the kinetic theory. Why? Well, in case you get a multiple choice question. All right, but basically we're only going to focus on one. I'm going to explain one in detail, which would be number 3. But let's just run through them. All right, number 1 says that the distance between the molecules of a gas are much larger than the width of those molecules in particular. So pretend you had a container, and each of these little dots represented a molecule. What we're trying to say is that the width of this particular molecule is much smaller than the distance between, let's say, these two adjacent molecules, or these two molecules, all right, or these two. Hopefully that should be clear. The next thing says that the gas molecules are in random or constant random motion. All right, they're moving all about in all directions totally randomly. I'll just draw a couple of vectors in there. All right, they're moving all about. And actually, I'll jump to number 4, all right? And as they're moving all about, you might say, well, won't they collide into one another? Sure they will, right? Not only will they collide into one another potentially, but they might also collide into the edges of the container. But all of those collisions are deemed to be perfectly elastic, all right? And you guys have studied momentum now, so that should be fairly straightforward. And then now, last but not least, number 3, is that it says that the average kinetic energy, all right, is determined by the temperature of the gas, and basically exclusively by the temperature of the gas. So let me explain that one a little further. So let's take a look at one of the equations of the ideal gas law. All right, so one of them is PV equals capital N times KT. If we remember, this stands for the pressure of a gas. This is the volume of the gas. Capital N represents the number of molecules within that gas. K is the Boltzmann constant, and then T is the temperature of the gas, okay? The pressure, if we remember, it's going to be in Pascal, right? The volume then is in cubic meter. And remember, is just the number of molecules, The K is the Boltzmann constant. This you got to remember, 1.38 times 10 to the minus 23. I think it's joule per Kelvin. And then temperature is measured in kelvins, okay? Now there's another formula, so this is 1, all right? This is ideal gas. There's another formula here that is a quasi-ideal gas, quasi-kinetic theory, all right? This formula states that the pressure of a gas multiplied by the volume will equal now 1/3. That's a 2, I don't know. Just seeing if you're paying attention. 1/3 multiplied by the number of molecules within the gas multiplied by the average mass of a molecule multiplied then by the average velocity of those molecules squared. All right, so again, pressure is in Pascal, volume here is going to be in cubic meters, and we know what that represents. That's the same thing as before. M is the mass of a molecule, or a single molecule, and this V represents the velocity, right, of a molecule in the gaseous mixture, okay? So what we notice now between these two formulas is that we have two terms that are the same, right? We have P times V being the same in both. And if those are both the same, and they both equal some other term, then I can set those terms essentially equal to one another, right? I can set this term equal to this term. So let's do that, and let's see what happens when we do that. So now we have capital N times KT, right? The number of molecules in the gas multiplied by the Boltzmann constant multiplied by the temperature shall equal now 1/3 times the number of molecules in the gas multiplied by the mass of a particular molecule multiplied by then the velocity, the average velocity of those molecules squared. So notice what we can do mathematically here, right? We can simply cancel these n's, okay? Now, that would leave us with the Boltzmann constant times T would equal now 1. Why did I do 1/2 again, guys? I'm just seeing if you're paying attention. I don't know. For the life of me, I was doing refraction today with optics, and I kept saying diffraction. Every time I said I'm just gonna electrocute myself every time I say it. Hopefully I won't say it again. Yeah, don't electrocute yourself. That's just a joke. All right. So here's what we have left. Okay. So now remember, we know that kinetic energy is a function of velocity. Right, so I'm just going to write that over here. Hopefully that formula is familiar It should be memorized, all right? And you might not have seen it for a while, but this should look familiar, right? So what I'm going to do here is I can do a couple of things. So first thing is, let me solve this for v in and of itself. Now I know I have a v squared here, and I can just solve this whole thing then for v squared and plug it on in to this equation over here to show you the relationship. But what I want to do is I actually want to solve this thing first for v. All right. What that means is now essentially I need to get these two terms, the 1/3 and the m, on over to the left-hand side. Okay. So you got to multiply this side by 3, right? And then this side by 3, and then you have to divide out the m, right? So that they cancel. Okay. Another way to look at it, which might be helpful, is let me just reorganize this slightly. And let me just put, this is essentially multiplying something by 1/3 here is the same thing as just simply dividing it by 3. Right? Those are the same. And now if you look at it this way, basically I just take whatever in the denominator on one side, bring it up into the numerator on the other. Whatever in the numerator on the right-hand side then goes into the denominator on the left. So I'm going to put a little fraction. And voila, right? Here it is. Look, I just solved for it. Okay? I just solved for at least v squared. Now, if I want to find just v alone, what do I have to do? I got to take the square root of both sides, right? And if I take the square root of both sides, I'm not going to simplify this whatsoever. I really can't, right? It just becomes the square root of 3 multiplied by that Boltzmann constant times temperature, all divided by then the mass of a particular molecule. That will equal now, essentially, just v. Now, what I wrote down over here is important. Consider that the v sub RMS, meaning the root mean square, that's what RMS stands for, root mean square. Consider that the root mean square velocity is simply the square root of the average velocity here squared. All right, so what I'm going to do is I'm just going to now restate this as v sub RMS in case you need that formula. So this is something else important to know. Now, what we realize here is that the velocity, the essentially root mean square, the average velocity of the particles, okay, in a gas is directly a function of the temperature here, right? You might say, well, it's also of the mass. Well, yes, but, you know, if you have a certain container of oxygen molecules and you try to change the conditions here, assuming you don't change the moles of oxygen, will the mass, actually, even if you were to change, even if you were to change the moles of oxygen, does the mass of a molecule of oxygen ever change? No. Right? It doesn't change. It's still O2. I don't care if you have 50 moles or 2 moles. It doesn't matter. Right? It's still going to be whatever the number is. Now, the only thing then that's really allowed to fluctuate here is the temperature of that gas. And that's what we're trying to state here, that the temperature basically is directly related, right, to the velocity. In other words, if I fluctuate the temperature, the velocity will change. And then we say, well, wait a minute. Well, if the velocity changes, doesn't that mean that the kinetic energy over here changes? Because I know that formula. And yes, it does. Right? Yes, it does. So how we now can write, so now what I'm going to do is I'm going to do that substitution. So basically here I have the kinetic energy is equal to now 1/2 multiplied by m, then multiplied by my velocity squared. Now don't worry that this says v sub RMS and this says just v. It's don't get too caught up with those subscripts. They're basically the same thing. So this would then be square root. So this would be square root then of 3 times kt all over m, and this whole thing then is squared. Realize all I did was I basically substituted this whole thing on in for v here. Okay, that's all I did. So now, and let me put that in a different color. All right, so let me just put that in a different color. So I substituted this whole thing in for the v over there. So now let's continue with the math a little bit. So we realize we have now the kinetic energy is equal to then, when I square a square root, what happens? Well, I can't hear you, so I can't tell if you're right. But if you said it cancels the square root, essentially you'd be correct. Right? This is 1/2 times m. Then multiplied now by 3kt all over m. And now let's just simplify this. So now we have the kinetic energy being equal to, the masses would cancel, and that's basically all, right? Now I would have essentially 3kt all over 2. And if you just wanted to say, instead of all over 2, you just wanted to put the 2 over under the 3, that's fine too. 3/2 times kt, it doesn't matter, they're all the same. And now, lo and behold, here we have now finally proven more or less number 3. that the average kinetic energy here, or the kinetic energy of the particles within a certain gas, is simply a function of just the temperature, right? K is the Boltzmann constant. So that's not changing, all right? It's just the temperature. So in total here, what I would highly suggest you do is you memorize now these formulas that I'm going to put a nice little star next to. This one you should memorize. This one you should memorize. This one you should also memorize, and this one. Okay? Some of you may have, cheat sheets available on the test. But when I say cheat sheet, I don't mean literally, they allow it, so you're not cheating. But you're allowed a formula sheet. I highly recommend that you know these formulas without that formula sheet. You should actually be doing enough practice where you don't have to sit here and memorize these formulas. You do enough practice where you're using these formulas all the time and they're kind of just memorized by virtue of doing the problems, by you seeing them so much. All right, if you're sitting down and you're saying to yourself, all right, great, I got to put this on a flashcard, put this on a flashcard, put this on a flashcard, and put this on a flashcard, that means you're not doing enough actual practice. Okay? So don't study that way. Do problems. Many, many, many problems. I actually guarantee it. I bet if you did all the problems in the textbook, you'll get an A. It's so simple. It's so simple in theory, but so hard in practice. All right? So just practice. Practice, practice, practice. And then practice some more. All right, let's move on to some more. Let's move on to now some examples of how we can apply these concepts. Neon and argon gas are placed individually into two identical containers at identical temperatures. On average, how many times faster is an atom of neon moving relative to argon? All right. So let's just, draw a quick picture. We really probably don't even need one for this, but let's just gain a little intuition. So we have neon, let's just say, in this particular container. All right. Actually, we have a whole bunch of neons, right? I mean, not just one. There's going to be many, many of them. That's N2. I don't know what that is. Here's neon. Right there we go. A whole bunch of neon atoms. And then we're going to have an identical container, same size, with, that doesn't look like the same size, does it, guys? No, it does not. So you know what we're going to do? We're actually going to make it the literal same. Okay. So now we're going to place inside of this container some argon. All right, Ar, 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 Ar. And it tells us that these containers are identical, so they're basically identical in volume, and also they are at identical temperatures. But the problem doesn't mention what it is. Right? We do know that this temperature is going to be some value. You can call it 100, 1,000. It probably doesn't matter. Right? So if you wanted to plug in a number, you probably could. But I'm going to just leave it alone for right now. I'll call this T1, or this could be the temperature of the neon. And this is the temperature of the argon, all right, Ar. We don't know what they are, but we do know that they equal one another, that the temperature of the neon will equal the temperature of the argon. All right? So basically, I'm just kind of writing down whatever the problem's mentioning so far, right? Nothing fancy. Now, in order to now solve this, it says how many times faster is an atom of neon moving relative to that of argon? When they're talking about on average, how fast something is moving, it's basically velocity, right? They want us to find velocity. Now, in terms of when we're finding velocity of gases, it just becomes a special word. We use the root mean square velocity. What does that exactly mean? It's just the average, basically. All right. It's a little more complex than that, but I think just consider it to be the average. All right. I mean, it is the average, but it's there's a certain distribution to it, and anyway. So I basically need to find the ratio of the velocity of neon relative to that of argon. All right. That's also what I wrote down here. How many times is kind of a key phrase for ratio. Anytime they say how many times faster, how many times more, how many times less, whatever the case is, it's basically a ratio that you're going to look to set up. So in other words, we're looking to solve for the root mean square, or the average velocity of neon relative to the average velocity of argon. All right. This is what we're looking for, this ratio. Now, in order to find this ratio, all right, I also notice that the root mean square velocity is equal to this whole mumbo jumbo. And remember, we derived basically this formula just a few moments ago. All right, so you can do that again if you like here in the problem, but I'm going to skip that step just because we've done it already, right? Basically, all you're doing, remember, is just you're setting, since these are both PVs, you're setting now this term in that equation equal to this term in that equation, and then you're simply just solving for V sub RMS. That's how it arose. All right, so now basically what I can do is write in each of those terms into this ratio, right? The numerator here represents the root mean square velocity of neon. Therefore, I could write square root of 3 KT, and that's, by the way, the temperature of neon, right? Divided by then the mass of a molecule or the mass of a single atom of neon. In this case, neon exists in its atomic state, and therefore we're talking about the atom of neon. Okay, then I can do the same thing now for the denominator, right? Square root of 3 multiplied by the Kelvin temperature multiplied by the temperature of argon, all then divided by now the mass of a single argon atom. Okay. So now what we can do, and now this is just kind of some algebra, since both the numerator and the denominator have a square root, we can basically just put a big old square root over the whole thing. All right. In other words, I'm going to just write, I'm going to drop the RMS for right now, just because it's too much writing, I think. And I don't want to confuse too much. But these are, all the velocities here will be root mean square. So basically this is now square root of 3 K temperature of neon divided by then the mass of neon, all then divided by overall 3 KT of argon divided then by the mass of argon. Now I know some people's brains are probably ready to explode at this point looking at this fraction within a fraction under a square root. Just bear with me. All right, I promise this, I'm going to make the math here as easy as I possibly can. So let me just make that square root a little larger. Now, if you remember back to math, if you have a fraction numerator value and a fractional denominator value, you can basically then multiply the numerator fraction by the reciprocal of the denominator. In other words, we can do something like this. Big square root still. Okay, I'm going to take the numerator fraction of 3K T sub Ne, all divided by then the mass of neon, multiplied now by the reciprocal of this denominator. So it's the mass of then argon, all divided by then 3K, the temperature of argon. Now what's interesting here is, notice how we can easily see now how things cancel. The 3 goes bye-bye, Boltzmann constant goes bye-bye. And what about the temperatures? Well, they're the same, so they also go bye-bye, right? And what are we actually left with? We're left with a very, very simple square root, okay? And I think what we're going to do is I'm going to just erase some of this over here for right now, because I realize that I'm writing quite large. So let's just move all this work on over to here. And we can now basically simplify this fraction to now just being the square root of the mass of argon over the mass of neon. Okay? So, beautiful. This is actually what I need to solve for now. Doesn't this look so much nicer? Now, they didn't tell us the masses, though. And you might say, well, how am I going to solve this? Well, either they're going to give it to you, or you're expected to, you might have a periodic table, and you're expected to look up these masses on the periodic table, aka the molar masses. So when you look up neon on the table, I'm going to write it up here. When you look up neon, the value you will obtain is roughly 20.18. All right, gram per mole. It's going to be the value. And when you look up argon on the table, that value is going to be roughly 39, I think it is 0.95 gram per mole. Now, the interesting thing about this is that you might say to yourself, well, wait a minute, don't I need to, in terms of the mass here, shouldn't it be in kilograms? And don't I need the mass for a single atom of argon? And my answer to that is yes, we do. Okay. However, since these all have the same units, right, we can actually simply just plug in these values and solve. Also consider that we are finding a ratio. And by nature, a ratio is unitless, right? What would the units of velocity divided by the units of velocity be? 1, right? They cancel. Meter per second divided by meter per second. Meter per second divided by meter per second is what? 1. They all cancel. It's 1. Right? So we can go through all that complicated mess of doing our conversion and getting to kilogram per atom. I'm not going to do that here because we don't need to. Okay? Just remember, it's a ratio. So as long as the units are the same for both of these, I can literally just plug them on in. Okay? In some of the other videos I do the conversions. I'm just showing you different flavors. And then you can pick what flavor you like. So this is now the square root of the mass of argon, which is going to be 39.95, then divided by the mass of neon, which is 20.18. The units would have all canceled. And now all I'm going to do is plug this into the calculator. Square root of 39.95 divided by 20.18. And again, taking the square root of that, we get about 1.407 or 1.41. So this is going to be equal to about 1.41. And now, again, what did we just solve for? Well, we basically just solved for how many times faster neon is moving than argon, right? Remember, this value here, and what happened to the decimal? I got to take that with me, right? This value here represented the velocity, the root mean square velocity of neon relative to that of argon. All right? And this is the overall answer. Okay? Now, next part. Are their average kinetic energies the same or different? Now you might say to yourself, well, average kinetic energy. I remember that, right? I mean, we just looked at this formula. Kinetic energy is going to be equal to 1/2 mv squared. You might say, well, wait a minute, if their velocities are not the same, right, as we totally saw here with the ratio, as long as this didn't work out to 1, that means they were not the same. If the velocity is different, then the kinetic energy should be different. Well, yes, but you made an assumption there. The assumption is that the masses were the same. But you know that neon is not the same thing as argon. They are two totally different things. They contain a different number of protons, neutrons, and electrons. And therefore, since their number of proton, neutron, and electrons are different, their masses are probably different as well. Right? It's like kind of saying, I have a bag of potatoes, 10 potatoes, and then I have another bag with 100 potatoes. Let's assume that the potatoes are all the same. What bag weighs more? Obviously the one with 100, right? So it's the same idea. So the masses aren't the same. So you cannot make that conclusion simply. All right? But to help us answer this question, we can do one of two things. Either you can memorize this down here at the bottom, that the average kinetic energy is determined exclusively by the temperature. And what that means is that if the temperatures are the same, the kinetic energies will be the same. That's fine. And that would be, so, I mean, there's the answer. But I would suggest you know this formula. And we just took a look at how this formula came about just a few minutes ago, right? And this formula tells us exclusively that the kinetic energy, or the average kinetic energy, and I should be very specific here, the average kinetic energy of a particular atom or of a molecule, all right, of a single atom or a single molecule will be equal to 3 divided by 2 multiplied by the Boltzmann constant multiplied by the temperature of that atom or molecule. Okay, the average temperature of that atom or molecule. So notice, in this formula, there actually is no mass involved. This formula, though, is a formula specifically for gases. Okay? So we can answer that question by just looking at the formula. If the temperature is the same for both gases, then the kinetic energy will be the same. There's nothing to really calculate. All right? It's more of a concept. Okay, let's take a look at the next problem. 5 moles of oxygen gas and 2 moles of carbon dioxide gas are placed in a rigid container at 45 degrees Celsius. Calculate the average kinetic energy and root mean square velocity of each molecule of gas. Okie dokie. So we have a container, right? Let's just sketch a little picture. Doesn't matter. Actually, I think it's spherical, right? That's going to say that in the next part. So we have a spherical container. And within this, we're going to place 5 moles of oxygen gas, and we're going to place 2 moles of carbon dioxide, all right, gas. And we know the temperature of this container, and therefore the gas inside of the container, we'll assume it comes to thermal equilibrium. The average temperature of the molecules here will be 45 degrees Celsius. So the temperature here will be 45 degrees Celsius. However, you know we need things in Kelvin here, right? We got to convert this to Kelvin by adding 273 to that. And let's just calculate that quickly. So that would be 3, that would be 1, and 8, right? 318. Okay, 318 Kelvin. All right, so that should take care of that. Now, let's take a look at the first part. It says calculate the average kinetic energy of each molecule of gas. Okay, so remember, let's take a look at the kinetic energy formula over here, kinetic energy for gases. It says that the kinetic energy of a molecule or an atom of gas, depending upon what type of gas you're talking about. Oxygen gas is diatomic, and therefore it is a molecule. It contains more than 2 atoms. It contains it contains more than 1 atom. It contains 2 atoms of oxygen. Carbon dioxide is also molecular. It contains 3 atoms. Okay? So basically, I'm going to frame this equation as saying the kinetic energy of a single molecule of oxygen gas will be equal to 3 divided by 2 multiplied by the Boltzmann constant multiplied by the temperature, the average temperature of that single atom or molecule. Okay, and in this case, it's a molecule of oxygen. So in order to find kinetic energy, all I have to know is the temperature, the average temperature of that particular molecule I'm talking about. Now, it tells us that both, oxygen and carbon dioxide are both of this temperature. So what does that mean? That means they're both going to have the same kinetic energy, right? So the kinetic energy of, let's say, oxygen, O2, would equal 3 divided by 2 multiplied by our Boltzmann constant of 1.38 times 10 to the minus 23rd, then multiplied by the temperature of that particular atom or molecule. In this case, it's a molecule of oxygen. It's going to be 318 degree Kelvin. All right, 318 Kelvin. So now when I do the math here, let me just scoot this up just ever so slightly. So now when I calculate the kinetic energy of O2, right, we just take out the calculator. 3 over 2 times then 1.38 times 10 to the minus 23 times then 318. And here we get 6.58. So now here we have 6.58 times 10 raised to the negative 21st power. All right, 21. And that the units here are joules. Okay, you can just memorize that. I mean, we could follow how the units work out and all this, but honestly, if I start placing units in here, to me, it gets way too busy. I like to just kind of memorize that, and it's easy. You should be doing enough practice where you do memorize that. Energy is joule. Anytime you see energy, it's joule. All right, assuming you place in the standard units, like Kelvin, and the Boltzmann constant is just the standard number, but it's in joule per Kelvin. All right, so that's the kinetic energy of oxygen, right? Of a single oxygen molecule. Now, we would do the same approach for carbon dioxide, but we know already that carbon dioxide's number here in terms of its temperature is going to be the same thing. So I'm not going to waste the time we'll just write it out. So kinetic energy of CO2 is going to be equal to 6.58 times 10 to the minus 21 joules. That's the kinetic energy of carbon dioxide there. Easy peasy. Let's take a look at the next. And then it says the root mean square velocity of each, right? Okay, so now I have to do root mean square velocity, so that means I'm going to be using this formula. Okay, remember that formula came about by simply setting this part of this equation equal to this part of that equation. Why can we do that? Because the PVs are the same. And then we just solved it for the velocity when we did that. All right, so here we have the root mean square velocity of, let's say, oxygen, all right, will be equal to the square root of 3 multiplied by the Boltzmann constant multiplied by the temperature of that oxygen molecule, the average temperature, all then divided by the mass of an average oxygen molecule. Well, not even average. I mean, they should be all the same, but then again, there are isotopes, right, as you know, and they might not be exactly the same. So, well, it actually is the average. All right. Anyway, now that I talked myself out of it, then talked myself back into it, we now need to look this up on the periodic table if it's not given. All right, so basically O2, we would know oxygen is about 16, right? It has about 16 grams per mole, but since you have 2 oxygens, the molar mass here is going to be about 32 grams per mole. right? And CO2 now, you have 2 oxygens, so it's 32, plus then you have 1 carbon, which is 12. So now you're going to have 44 gram per mole. Right? Now in this case, as opposed to the other problem we've just done, let me make this a little clearer, we do need to convert this into kilogram per molecule. All right, there is no way around this one now. Okay, reason being is because I need to find the root mean square velocity, and I'm not using a ratio. I'm not doing a ratio or anything like that. So I gotta find the right unit here. All right, what I'm going to do down here is I'm going to do the conversion on down here. All right, so I'm going to do it for one, and then we'll just calculate the other. So we got to take 32. I'm going to do it for oxygen. 32 grams per 1 mole. Remember, anytime it's per anything, it's always per 1 of that anything. So now gram will go on the bottom and kilogram on the top. Remember, standard units in physics will be kilograms, so I got to cancel the gram. And you know that there's 1,000 grams in 1 kilogram, so see you later, gram. Now, if I were to stop here, I would have kilogram per mole, but I don't want kilogram per mole. I need kilogram per molecule. Why molecule? Because I know I'm talking about oxygen, and oxygen exists as a molecule. So that means I got to put mole on the top, and I got to think about if I know a relationship then between mole and what I'm going to write here, molecule. And do we? Yes, we do. Right? It's actually Avogadro's number. So you have to have this memorized, that 1 mole is equivalent to 6.02 times 10 to the 23rd molecules. All right? And now this is what we need, basically. The moles will cancel, and leaving us with kilogram per molecule. And that's what we need. We need the mass of a single molecule. So 32 divided by then 1,000 times 6.02 times 10 to the 23rd. So this is going to be 5.32, about 5.32 times 10 raised to the negative 26th. Negative 26, and that is kilogram per molecule. And what we're going to do, again, when you plug in the value here, we're just going to plug in kilogram, all right? But, you know, because we're talking about the mass of a single oxygen molecule. All right. So now here, let's just start plugging in the values. So we have the root mean square velocity of oxygen will be equal to then square root of 3 multiplied by that Boltzmann constant of 1.38 times 10 to the minus 23rd, multiplied then by the temperature of oxygen, which was about 318. The average temperature is about 318. All divided now by the mass we just found, so about 5.32 times 10 to the minus 26th. And now all we have to do is calculate. All right, so I'm going to use the exact value for the mass when I do it. So your answer might be slightly off the mine if you use the rounded, but you know, we should be within a very close ballpark. So square root of 3 times 1.38 times 10 to the minus 23rd, multiplied by 318, divided then by 5.32. Well, I just mentioned I was going to do the exact, right? And then I wound up rounding. Okay, now I messed this whole thing up. Good for me. One more time, guys. One more time. So square root of 3 times 1.38 times 10 to the minus 23rd, multiplied by 318, then divided by, now let me go searching for that exact number, and there it is. And here we have about 498 or so. 498. And this is going to be meters per second. And that is the average root mean square, or the root mean square velocity of the oxygen molecule. So now we would do the same thing for carbon dioxide, right? The only thing that would change, focus down here on the bottom left, guys. Instead of using 32 now, what are we going to use? We're going to use 44. And then when we calculate our new value here, the only thing that's going to change then is the denominator value over here, right? So really, I'm going to highlight this. This is going to be the number that's going to change because I'm using now a different molar mass. Okay, so let's do that. So we're going to do 44 divided then by 1,000 times then the times Avogadro's number in the denominator. So I get about 7.3 times 10 to the minus 26 as the kilogram per molecule. And now I'm just going to plug everything into that formula again. So it's 3 multiplied by the Boltzmann constant negative 23rd, then multiplied by the temperature of 318 because the temperature is the same, and then divided out by that mass. And we realize now that the root mean square velocity, RMS, of then CO2 will be about 424 meters per second. Now notice it's less. And why is it less? Well, look at the way the formula is set. If the numerators are all both the same when I compare oxygen and carbon dioxide, which they are, and the mass of carbon dioxide is greater than the mass of oxygen here, that would cause this whole value to go down, right? Bigger denominator, smaller overall result, and therefore smaller velocity. And that's exactly what we see over here. So that would conclude that part, all right? And now, last but not least, let's see, calculate the gauge. Okay, so now let's maybe back out of this a little bit, okay? Hopefully I don't think I'm going to need any of this. So let's just erase some of this work, okay? Hopefully I don't. Well, we'll see. All right, we'll see. So how you guys doing? You guys having fun yet? Physics isn't so bad. It's not so bad, it just takes a lot of time, right? It requires a lot of time. But such is anything if you want to become good at it, right? Learning an instrument, learning how to play a sport, playing video games, right? I mean, yeah, it doesn't matter. It takes time. All right, enough of the lecture. Back to the problem. If the container is spherical with a radius of 0.125 meters, calculate the gauge pressure inside of the container. Right, so I need to find the gauge pressure. All right, so what we need to do is they also tell us that it's tough to draw a three-dimensional sphere here, but they also tell us the radius, right, of this particular sphere. And they tell us that the radius here is going to be 0.125 meters. Now, what the radius allows us to do is calculate the volume of this sphere. So we would have to know the volume of a sphere. You might have to look that up, or they might require you to memorize it. I don't know. But the volume then of a sphere is going to be equal to 4/3 pi r cubed. Okay? And basically, whatever the volume of the sphere is also the volume of the gas that is inside of it. Why? Because the gas expands to fill up the entire volume of the container that it is in. All right? So that means that the volume of the gas inside of this container is equal to and the same thing as the volume of the container itself. So let's calculate that. So this is 4/3 pi multiplied now by r cubed, or 0.125, and it's in meters, so I'm good. I'm just going to plug it all in. So let's calculate it. So it's 4/3, 4 divided by 3 times pi times then 0.125 cubed. And here we have a value of about 0.00818 or so, 0.00818, and this is cubic meters. All right, cool. So I'll box this in, we'll keep this on the side. Now we know the volume of the gas. We know the temperature of the gas, right? I'm just going to simply move this on over now. I'm going to start lining up my variables, right? We know the temperature, okay? What else do we know about the gas? Well, we also know the number of moles. Now remember, we're trying to find the gauge pressure inside the container. So what that means is that I have to know the total amount of moles of gas. I don't care if it's oxygen or carbon dioxide, it doesn't matter. All right? I need to find the total number of moles. So how do we find the total number of moles inside of the container? Well, we just add them together. Right? It's simple. So that's going to be 5 moles of oxygen plus then the 2 moles of carbon dioxide. So the total number of moles inside of the container is 7. Okay, and what that means then is that if I want to find the total pressure, or I should say this, that means I can find the total pressure. Why? Because I know the total moles, I know the overall temperature of the entire tank, and I know the overall volume of the entire tank itself, right? So now I'm just looking for a formula that will relate all 4 of these variables to one another. And we realize that up here on the upper right-hand side, we have something that might be nice. Except not exactly, right? What do we notice that's missing here? We notice that it doesn't have the moles. So you might remember it, and I'm kind of testing you here to see if you do remember the formula, because we should be doing enough practice where you have them memorized. We need the other formula, right? So I'll just erase this for right now, and I'll write it on the bottom. We need the P I mean, you can use this. You just have to convert then the mole here into molecule. But why? Why? Right? Why? Let's just do it. Let's just do it like this. PV equals nRT. So now if I use that formula, right, PV, the pressure of the gas multiplied by the volume of the gas is equal to the total number of moles of that gas multiplied then by the R constant multiplied by then the overall temperature of the gas. I need to find pressure, so all we have to do is just divide out the volume. And we realize that the pressure here will be equal to the mole times R times T all over V. And now I just have to plug in my values. So let's see, pressure will be equal to, this will now be the mole of 7 multiplied by R, which is going to be 8.31, times the temperature, which is 318, all then divided by the volume, right? And the volume, as we found before, is going to be about 0.00818. So let's plug it on in. So we have 7 multiplied by 8.31 times then 318, all divided by then that answer of 0.00818, and we get about here, so the pressure is going to be 2.26 times 10 to the 3 times 10 to the 6. All right, and this is in pascals. So that's the pressure, but is that now the gauge pressure? No, right? Remember, the pressure inside of these formulas, inside of the ideal gas formulas, calculate absolute pressure. So that's not a big deal because we have a nice little formula here that converts absolute to gauge pressure. So I'll just write it down here, that gauge pressure will equal the absolute pressure minus then basically atmospheric pressure, 10 to the 5th. So all we have to do is just plug it in. Gauge pressure will be equal to then 2.26 times 10 to the minus 6, excuse me, not minus 6, positive 6, minus then 1.013 times 10 to the 5th. And what do we get when we do this in the calculator? Let me just move this up ever so slightly. So we get now gauge pressure will be equal to, I'm going to use the exact number, subtract out then the 1.013 times 10 to the 5th, and we have a value of about now 2.16 or so, 2.16 times 10 raised to the, should be 6th again. And this is in Pascal. All right, so quite a high gauge pressure. All right, guys. Hey, thanks for tuning in. All right, if you're still with me, thank you very much. I really do hope this video helped, and if it did, give us a hand. Tell your friends. Hit the subscribe button and the like button if you can too. All right, and if you can't, all right, no big deal. You know, we'll get you next time maybe. All right, I'm gonna try to earn it from you. I'm gonna try to earn it. All right, take care.